All right, chemistry students. So we have just been talking a lot about molecular compounds, ionic compounds, also known as molecules or molecular compounds. We've learned about what they are, how they are different from ionic compounds, in that they share electrons instead of giving and taking or donating and accepting them. And we've learned how to write their names, and we've learned how to write their formulas. So there's one more thing to learn. I'm going to say right off the bat, we're going to talk about Lewis structures. This is not absolutely crucial for this unit. So if this is the thing that you're a little bit confused on, don't worry too much. It's going to come back a lot for unit 7, which is all about bonding. So we're going to learn way more about this. However, I think it's really good to start thinking about it now and to start learning it now, because it will really help cement this idea in your head that covalent molecules share electrons. This is really, really important. And that ionic molecules or ionic compounds don't. They're not molecules. They don't behave in this exact same way. So we're going to go through this. Now, this is not in your notes. If you take out your blue notes, you will not find any section on this. And that's cool. We are actually going to go to the unit packet. So let's go to the unit packet right now, and I'll start showing you exactly what we're looking at. Okay. Oh, there it is. All right, so this is our unit packet. We flip to the front, et voila. All right, we are on page 3 right here. I'm gonna zoom out just a little bit. That could be helpful. Maybe we can see the whole thing just a little bit better. Is that good? That's not terrible. I can do better though. Okay, so we are on currently on page 3. Page 3. And we're also going to look at page 4 and page 5 and page 6. So one thing about these notes, these packet pages, you don't actually have to do all of it. Pages 3 and 4 and 5 are actually all just notes. So they're just here just to kind of teach you this. The only actual page you have to do is page 6, okay? And I'm going to help you. Actually, you may have to do a little bit on page 4. So some of these problems. I'm going to do a couple of them for you, and I'll also do a couple of them for you on this page as well, and then you'll just do the rest. So let's go through. Let's start working on this. Okay, so this gives you a really nice outline. I just want to kind of go through and explain what's happening here. So the first thing is that we already know what a Lewis electron dot structure is. We learned about it last unit. And it's the number of valence electrons around the symbol. So these are some really great examples of what Lewis electron dots should look like. And if you remember, on your periodic table, you have written down these numbers. So for example, sodium is right here on the periodic table. It's the first group, and it has this number 1, so that means it has 1 valence electron. Calcium is here. You go up, it says 2, so it has 2. Phosphorus, for example, is right here. You go up here, we wrote down 5, so it has 5. You'll also notice that the way they've drawn these is there's like little invisible squares around each of these, and that the dots line up really nicely around these squares. And the other rule to remember is you put 1 on each side before you start doubling up. So aluminum, there's 3, so that's 1, 2, 3. You can write this other ways. If you wanted to write aluminum like this, that's fine, no problem. There's just 1 on each side. This is a big fat no, because it has 2 paired off before there's been 1 on each side. So that's the only thing you really have to remember. So just as a quick refresher, let's just do one of these. Let's do the first one. So K is potassium. So let's find it on the periodic table. It's right here. We go up. It only has 1 dot on it. So the symbol is simply that, or this, or this, or this. They're all fine. They all work. Okay. So if you need a refresher on Lewis electron dots, you might need to do that. You can always ask me for more help. but I think it's pretty straightforward and pretty simple. So let's talk about bonding. These are really important for that. So essentially, the idea behind this is that we know that in covalent bonds, atoms are sharing electrons in order to fulfill their full valence shell, which we generally call the octet rule. So when they do this, they're looking for extra electrons to fill up so that they have that complete shell. For hydrogen, they just need one extra electron. For all other elements, they're going to need however many they need to have all 8. So they can share, they come together and share them. The way I kind of think about this is like connect the dots. So let's take a look at some of these examples. Okay, so this first example, they are trying to build H2. Okay. So here's what they did. They figured out that there's 2 hydrogens in this compound. So they drew both hydrogens here and the 2 valence electrons. Let me grab, maybe electrons are red. Electrons are always red. So there's the valence electron and there's the other one. Okay. They both need an extra. So the way I like to think of this is that you are drawing a line between them. This means that they're being shared. And it's being represented right here, that bond. The final drawing, you just take those 2 dots and you turn it into a line. Okay, so 2 dots equals a line. Okay, when they're drawing together, this is a bond to form a bond. All right, so kind of simple, right? So that is what a hydrogen atom or molecule looks like. An individual hydrogen atom is just by itself, but when 2 of them come together, they've got a little bond between them. You've probably seen drawings like this before in like movies and TV shows and stuff when they try to talk about science. Yeah, these models are they're really easy to make. They're great. Mostly in TV and movies, they make them, they don't do very good jobs. It's pretty fun. Okay, so let's take a look at another. This one is chlorine. So they are trying to make Cl2. This is the molecule that they're going for. So the first step is to draw the 2 chlorine atoms with their valence electrons. We can see that this chlorine has 7 and this chlorine also has 7. They each need 1 more to make the octet. So there's 2 unpaired electrons and all we have to do is share them. That's what this little bond represents here and the same thing there. So again, these 2 electrons coming together becomes that bond. So that's the Cl-Cl bond. All right. So that's page 3. So let's take a look and see if we've got more. Yeah, we've got one more here. Okay. Now, in chemistry, these are called single bonds. There's also something called a double bond, and that's what oxygen is here. So over here, we are trying to get O2. That's our goal. So they've drawn out the 2 oxygens. Each oxygen has 6 valence electrons, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. And it looks here like they each need 2 electrons. So what you can do is it's pretty obvious that you need to pair off at least 1. So that's like this little bondy doodle there. However, you can also do it again. There's no limit to how many times you can do it. Well, technically triple. Triple is the most you can do. This electron and this electron can also bond together. And that is the second bond. And it's this one here versus this double bond here. Okay. So in this case, this is called a double bond. And that's when you have 4 electrons being shared between 2 atoms. You can also have, you guessed it, a triple bond. That's when you have 6 electrons being shared. It becomes a triple bond. Okay. So let's go through an example together. Okay, bromine, this is great. All right, so a good first step here is let's draw the element. Okay, so we're gonna draw the bromine. So there's gonna be 2 bromines. We know that because of that 2 here. So I'm just going to draw these off to the side next to each other. And we need to figure out how many valence electrons there are. So bromine is over here. Oops. Okay. So bromine has 7. So let's draw the structure. Let me switch to red because I like red for electrons. 1, 2, 3, 4, 5, 6, 7. I like to draw it like that. And then let's do the other bromine. 1, 2, 3, 4, 5, 6, 7. So the total number of valence electrons is 7 plus 7 is 14. Okay. So now we just have to bond them together. It looks like these 2 electrons here are the ones that can get shared. So once we do that, that's the bond. So those 2 electrons were actually kind of like, they're like here and here. Like that. Okay, so we can double check to make sure that this makes sense. Each atom should have a total of 8 electrons around it. The bond, the little lines, count as 2 for both. So this bromine has 1, 2, 3, 4, 5, 6. The bond counts for 2, 7, 8. So this bromine has 8 electrons now. And then this bromine, 1, 2, 3, 4, 5, 6. Again, that bond counts for 2, 7, 8. 8 electrons. Okay. So both of them have their full octet valence of 8. The total number of electrons is 2, 4, 6, 8. That only counts once because it's just 2. Oh, sorry. 2, 4, 6, 8, 10, 12, 14. So we've got 14 electrons, and each bromine gets to have 8 that are surrounding it. Pretty cool, right? Yeah, I thought so. Okay, let's do, how about you guys try the rest? I'm going to end up doing, I'll probably have one more of these in the key. You guys can check these out. No, I'm going to do HBr with you. HBr is good. Let's do HBr. You guys can try HCl and N2 on your own. Okay, so HBr, same process. Let's go through it together. First thing, we know that there's 1 hydrogen and 1 bromine right there. So we're going to draw the hydrogen and the bromine. Once again, let's double check the number of valence electrons. Hydrogen is here, so it only has 1. Bromine, once again, is over here. It has 7. So this one just has 1. Bromine has 7. So it looks like we are going to draw, I'm going to try pink here instead. Let's see how that works. We're going to draw the line right there. So if we redraw this, oh, we should count the number of electrons. I forgot. Okay, so bromine has 7, hydrogen has 1. So it's 1, 2, 3, 4, 5, 6, 7, 8. So there's a total number of 8 electrons. So if we draw this, we got H. There's the line, the bond, Br. We can't forget those lone pairs of electrons. We call these lone pairs of electrons because they come in pairs and they don't bond. So they're kind of alone. We call them lone pairs. Yeah, I'll write that up here. These are lone pairs. Okay. So again, going back here, once again, hydrogen has 2 electrons from that bond, which is pretty much what we'd expect from hydrogen. I use E- to represent electron. A lot of people do that. Bromine has 2, 4, 6, 8 electrons, which satisfies the octet rule. In total, there's 2, 4, 6, 8 total valence electrons. So we are all good to go. All right. So if you want to pause the video and try out those other 2, please do so. And otherwise, we're going to move on to the next step, which is if you have more than 2 elements or more than 2 atoms that are coming together. So this is page 5, the last bit of our notes. Okay. So for larger molecules, you're going to do the exact same process, but it might take a little bit of tinkering to figure out how everything's going to work. So we are looking at this first example. The general rule here is figuring out which is the central atom. Generally speaking, whichever atom they list first is probably the central, not always. It's also whichever one has a lot of lone pairs of electrons that you can fit together. So what we're looking at here is COH2. That's our formula. Okay. H is always on the outside. You can always add them last because they can only ever bond to one thing. They have just one valence electron. Carbons tend to be in the middle. And there's a reason for that, because if you look at the periodic table, carbon has 4 valence electrons. So let's draw those in. 1, 2, 3, 4. It has 4 places that it can bond. So it makes sense that it's in the middle. It's actually why we need carbon for life, because it can bond with so many things. That's why it's the most important element for life. Okay, oxygen has 6 valence electrons. Hydrogen has 1. So I'm going to draw those in real quick. So now it's just a matter of connecting the dots. And what you'll see, this has a slightly different method of going about doing it, but it ends up being the same. I can tell right away that the hydrogens and carbons are definitely going to bond right there, and that this one is going to bond with the oxygen. The only problem now is that we have 2 electrons that are left over, and we can't have single electrons. We can either have lone pairs or bonds. So these are lone pairs, and they're totally fine, no problem. But what we have right here, what's a good color? Green. This is a problem right here. This little electron here and this little electron here. What we can do there is make a double bond. So this electron, it can move over. Electrons actually move very easily. These diagrams are static, it's not real life. So we can actually have these 2 bond together, okay? And when you do that, we can rewrite this really quickly for you. It'll look like this. There's the carbon. It looks like there's the hydrogen and the oxygen. And it looks like we've got 1 bond with each hydrogen. And it looks like we've got 2 bonds, a double bond between the carbon and the oxygen. And don't forget the lone pairs. I like to move them around sometimes just because. Okay. Pretty cool, right? So this example leads you through that exact same process. It just does it a little differently. If you want to read through it and you really like that method, it does work. One thing that we can also do is count the number of valence electrons. So carbon originally had 4 valence electrons. Hydrogen each had 1, so that's 6. Oxygen had 6, so that's a total of 12 valence electrons, total valence electrons. We can double check to make sure that this also has 12. 2, 4, 6, 8, 10, 12. 2 for each of the bonds, the single bonds. 4 for this double bond because there's 2 lines. Each line is 2 electrons. And then 2 sets of valence electrons. We can also check to make sure that each of the elements, each of the atoms has a full octet. Hydrogen has just 1 bond, which is perfect for hydrogen. It only ever has 2. It doesn't have 8. Carbon needs 8. So 2, 4, 6, 8, it has them all. 2 single bonds and 1 double bond, that works. Oxygen has 2 lone pairs, that's 2, 4, 6, 8 from that double bond. Okay, so this completely works. It totally is awesome. And that is a great structure, which if you notice, it's the exact same structure they ended up with the end here. I'll tell you one other thing, just for fun, just to throw it in there. We're going to learn a little, well, no, we'll do it later. Technically, this model, we can make it just a little bit better. It's good if you kind of make all the bonds evenly distanced from each other. Like right now, you'll notice that this is like a 90-degree angle and that's 180. You can actually rearrange it more like this to be just a tiny bit more perfect. It is not necessary by any means, but just for funsies, I thought I'd show you. I mean, really, these are pretty similar, but this one's a little bit better. We'll talk about that in Unit 7. Okay, so pause here if you need a little extra help. I'm going to connect some other videos you can watch, but let's do an example or 2 on the back. Okay, so here is how I go about doing these. My first step is I always start with whatever the formula is, and I write out all the Lewis structures. So I've got silicon. Silicon is right here. So it has 4 valence electrons. I like to think of this almost like a bank. Like almost like a, not like a word, kind of like a word bank. Yeah. Like here's all the little puzzle pieces and we just got to figure out how we're going to put them together. Then we have 4 hydrogens. So hydrogen, 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 hydrogen. Each one has 1 valence electron, okay? So looking so far at our totals, it looks like we have 1, 2, 3, 4, 5, 6, 7, 8 total valence electrons. So we want to make sure we end up with 8 at the end. So looking at this, it looks to me like if silicon were in the center and we put a hydrogen around each side, it would probably work out pretty well. So let's give it a go. Again, I'm just doing this more like as like a visual puzzle. Like that's where, it's like a connect the dots, like I mentioned before. However we can arrange it. And I'm gonna put all the valence electrons so they're oriented in the correct place. So I just copied them. So now we can see this bond here, this bond here, this bond here, and this bond here. And if we go back and count, each hydrogen has 1, 2 electrons from that bond. The silicon needs 8 and it has 2, 4, 6, 8. We have a total of 8 valence electrons. So it looks like that's a pretty good Lewis model. All right. Let's try another one. Let's do this phosphorus trichloride. Okay, so same process. Again, pause if you need to go through things again. I'm going a little fast because it's a video. Okay, so let's start with phosphorus. And we've got 3 chlorines. And we're just going to put our puzzle pieces off to the side so we can figure out how to put them together. Okay, looking at our periodic table, phosphorus has 5 valence electrons. 1, 2, 3, 4, 5. And chlorine each has 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay, so we need to figure out a way to arrange these. So it looks to me like phosphorus has 3 spots that we could bond things to, and each chlorine has 1. So it looks like if we put the phosphorus in the middle, that would be probably a good choice so that the others can bond to it. And I'm thinking like this because I'll show you. Phosphorus has this pair of electrons, and we don't really want to mess with that. So that pair of electrons, I keep switching colors, but oh well. This pair is good. We want to leave them alone. But then it has 3 single non-paired electrons. And let's make sure that the same thing is oriented correctly for chlorine. We'll put that single electron facing in the exact same direction. And then we just solve the puzzle by connecting the dots. That looks pretty reasonable to me. Oh, we forgot to count the valence electrons. Oh no, we'll go back. Okay. Here we had, each of these chlorines had 7. So 7 times 3 is 25. Plus 5, no, 7 times 3 is 21, pardon me. Plus 5 is 28. And let's make sure we still have 28. So we've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Ooh, did I miscount? Oh, it was 26 because I can't do math. Okay, 7 plus 7 is 14, plus 7 is 21, plus 5 is actually 26, not 28. See, I'm terrible at math sometimes. Okay, so again, it should have 26 electrons, and we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. That makes sense. All right, so that is what phosphorus trichloride actually looks like. And what's great about these models is that they really show you what these look like. It's not a 3-dimensional model, which is even better. We're going to learn about that in Unit 7, second semester, but it's much better than just looking at a static picture. Okay. Other weird note, in case you were wondering, I wanted it to be this kind of T shape because this lone pair of electrons kind of like takes up a slot. So if you're curious about why I didn't make it like a Y shape, yeah, you know, I didn't do it this way with the chlorides off to the side, because these electrons actually are, it's how many, it counts like a bond. So we wouldn't actually do that. This would be probably the best way of drawing it. Actually, there's a better way that's more three-dimensional, and there's also 3D models, but again, we'll get into those. So once again, give these a try. You have a couple more to do. All of the, I will tell you, all of these have a central atom. I'm even going to kind of give you a little hint. Again, the first one is always the central. So in this case, the carbon, the nitrogen, the carbon, and the carbon. If you put those, sorry, down there, you can see that carbon. If you put those at the center and everything else is around them, it'll work out just fine. There's some more complicated ones we can do where they form lines or circles. But for right now, I think that will do the trick. So your work on this one is, again, just to work on finishing up page 6. You've got 2 problems here on page 5. And then you've got a couple of quick Lewis models over here on page 3. And that's pretty much it. If you just do page 4, that's fine with me. If you want to skip the other ones, if you're really good, no, sorry, page 6. You can just do page 6 because this is the hardest ones that I can throw at you for right now. Again, if this is a little bit of a struggle and you're not quite getting it, this is not the main focus of the unit. The focus of the unit is writing formulas and names. If you can write formulas and you can write names, that is what's most important. This is icing. So it won't show up a ton on the test. It'll show up like once. So no big deal. All right. With that in mind, as always, let me know if you have any questions or you need any help. You can always email me, alicia.drapkin@tusd1.org.